Okay, hello everyone. So today we will continue our topic about interrupts. So last time or in last previous two lectures we have talked about what interrupts are, how they differ from polling, how they are better than polling to handle the events, and then we talked about how we can enable interrupts in Atmega 3284P microcontroller, 328P microcontroller, and we looked at timer related interrupts, and then also we had a look at external interrupts in the last lecture. So today we will continue this discussion. So the first thing that we are going to talk about is the interrupt priority. So let's assume a situation where you have two different interrupts arriving at the same time. For example, remember last time we talked about interrupts which can arise, software interrupts which can arise when, let's say, the timer zero overflow happens, right? Now, let's say I have configured timer zero to raise an interrupt when the overflow happen, and I have configured timer 2 to raise an interrupt when the value of the interrupt register, sorry, the when the value of the counter register becomes equal to the one of the output compare registers values, right? So it's mean that now two interrupts I have configured enabled two interrupts. Now consider the situation where the interrupt from the timer 0, the overflow interrupt from the timer 0, and the output compare interrupt from timer 2 both arise at the same time, right? Now, in this situation, we mean it means that two interrupts are active or raised at the same time. Now, how should we handle this, or how the microcontroller should handle them? So definitely microcontroller can handling them means that microcontroller needs to run their interrupt service routine, but microcontroller can run only one interrupt service routine at a time, right? Because we have a one processor, right? So it's mean the microcontroller need to choose which one of them should be executed, and how it is decided. It is decided based on the priority of the interrupt. So the interrupt, if there are two interrupts rising at the same time, the one which has the higher priority, ISR of that interrupt will be executed, and ISR of the other interrupt will not be executed, right? So, for example, the in context of the example that I just mentioned, if there is a timer zero overflow interrupt, right, and there is a timer two output compare match or interrupt, right? So their addresses are shown in this interrupt vector table, right? So where you need to store their ISRs. So for timer counter 0, the address is 16. For timer 2 compare match interrupt, the address is 8, right? Now, how we know that which one of them has the higher priority? So for that, we use the addresses, and the lower address mean the higher priority. So here, the address for ISR for timer 2, timer counter 2 compare match interrupt is 8, and the address for timer 0 overflow interrupt is 16. So it means since 8 is less than 16, so the compare match interrupt from timer 2 has higher priority, and that's why the microcontroller will execute the ISR of this interrupt, not the other one, not the timer 0 overflow. So in this table, priority is depends upon the addresses, and lower the address, higher is the priority, right? And higher the address mean lower is the priority. Okay, so that is how like if multiple interrupts are arising at the same time, how they are handled. They are the one which has the highest priority will be handled by running its ISR, and all others will be ignored, right? Ignored at that time point. But in the future, let's say if they again an interrupt arises, then again microcontroller will check which one of them has the highest priority and pick that one and serve that one. Okay. Now, uh, another situation can happen when we are serving the interrupt, which is like interrupt rising inside an interrupt service routine. So, uh, which is basically, let's say your timer zero interrupt rises or it happens, and then microcontroller starts executing its ISR, right? and it starts executing at this point, and let's say the size its ISR takes some time to execute because it has a bunch of instructions, and at the end you have return I statement, return I instruction, right? Return from interrupt. So let's say that when the timer is serving when the microcontroller is serving timer 0 overflow interrupt by running this ISR, and it is in middle of this ISR, let's say at this time point, another interrupt arises. Let's say the interrupt arises as its 0 input, right? Which we already have configured and enabled. Now, if the interrupt arises on this input while we are serving another, actively serving another interrupt, then what should we do, right? So for that, to handle this kind of situation, what happens is that whenever your microcontroller begins to execute an ISR, for example, the ISR of timer 0 overflow interrupt, so it will clear the I flag in the status register, which basically mean that I am disabling I am disabling the interrupts. So even if another interrupt rises, like let's say the push button on int 0 input is pressed from our example in the previous lecture. So since I is equal to 0, microcontroller will simply ignore it, will not process that interrupt, which means it will not run its interrupt service routine. And when at the end we reach at the end of the ISR, and the microcontroller executes the return interrupt instruction, then it will set I is equal to 1 again. And if this int 0 is the interrupt on the external hardware interrupt is still active, then microcontroller will serve it by running its ISR. So basically what we are saying is that interrupt and inside an interrupt is not allowed. Okay. You can do that, but the default behavior is that it is not allowed, but you can actually enable it by how, because when you start running ISR, you can put an instruction here, SCI set interrupt enable. So no, I think it is SIE, not SCI. So SIE, so set interrupt enable. So what it will do is that it will set I equal to 1. So it means that you are saying, okay, I want to serve the interrupts even when I'm running ISR of another interrupt. But then it is your responsibility to write the correct code and take care of the uh, handling the nested interrupts, right? But the default behavior is that whenever the microcontroller starts executing an ISR, it uh, it disables the global interrupt by setting I is equal to 0. So nested interrupts are by default not permitted. Okay, so uh, Uh, let's talk about another issue related to handling ISRs. So, which is about task switching and resource conflict. Resource conflict here, because since we are talking about microcontroller, so resources, our examples of resources are very simple. Basically, in this case, by resource we mean the register. So, register conflict, right? So, here what we are doing in this example is that we let me just first draw the figure to show you what we are doing, and then I can walk you through the code. So on the port C, we are sending the value of R20. So what we initially do is that we set R20 to 0 and send the value to the port C, output port C. And then in every iteration, we increment the value of R20 by 1 and repeatedly keep sending it on the port C. So which means that on the output port C, we will see the values if let's say you have connected a display. So you will see the values like 0, 1, 2, 3 and incrementing, right? But at the same time, we are also we are enabling the output compare interrupt of the timer 0, right? And what we want to do is that when the interrupt rises, output compare interrupt rises for the timer 0, what we want to do is that we also want to send the value on port D in an incrementing fashion, which means we want to have also displayed on every interrupt. We want to display on port D the values like 0, next time 1, on next interrupt 2, and on next interrupt 3, and so on, right? Again, before I walk you through the example, just keep in mind that this code is not written for at mega 328p, but this example is for, let me mention it here, assembly program is written for at mega 328 and not for at mega 328p. The two microcontrollers differ in their registers, but I mean, you will easily be able to understand the code because that mega 328 also have similar registers as that mega 328p with the similar functionality. I will explain. Okay. So now you know what we want to do. We want to, like on port C, we want to send the values in incrementing order like 0, 1, 2, 3. And also we want to set values on port D in incrementing order. However, the values which we are sending out on the port C, they are sent in a, they are sent in the main code where we are running the loop to like every time increment the value of R20 and send it to the port C. And the values which we send on the port D, we send them through by handling the interrupt or timer output compare interrupt of timer 0, right? So whenever an interrupt arises, we handle the interrupt, which means we run the ISR, and when we run the ISR, in the body of that ISR, we simply read the current value of the port D and increment it and send it back to the port D. Okay. So now let me walk you through the code. So what we are doing here is that, again, we are saying that we are starting our code at address 0 because this is the address from where the instruction is executed when we reset the microcontroller. So we are just simply putting the jump instruction there, which means that whenever we reset the microcontroller, this instruction will be executed and the control will transfer to this point after that, right? Jump main. The other thing we are doing is that at the address 0x14, we are putting the statement jump timer 0 compare match ISR. And why this address 0x14? Because this is the address where we have to place the first instruction of the ISR to handle the timer 0 compare match interrupt. And again, you can get it from the uh, vector table, right? Okay. Uh, then in the main program, what we are doing is that for in first four instruction, we are initializing the stack pointer. Then in the next instruction here, we are setting the port B5 as an output pin by saying that set the bit at index 5 of the DDR-B register. And then again, remember that this program is written for at mega 328, not for at mega 328p. In at mega 328p, we have register two registers, output compare register 0A and output compare register 0B, right? But in the at mega 328, you have only one output compare register, which is known as output compare register 0 for the timer 0, right? So what we are doing is that, and we are putting the value in the compare register. What is that value? We have 160. We load 160 into R20 and then send R20 to the output compare register 0, right? And then we configure the control register of the timer 0 by putting value of 9 in R20 and then sending that R20 to the control register. So here we are basically saying that okay, enable the you use the timer in the CTC mode and use the internal clock without any prescaler. Again, remember that in at mega 328p you have two control register TC TCC R0A and TCC R0B, but in at mega 328 you have only one control register TCC R0. So again, you remember that if you want, you can modify this example for at mega 328p by just putting the appropriate values in, like for example, output compare register 0A and then putting appropriate value in timer and counter control register 0A and timer and counter control register 0B. Okay, so that's not a big deal. I didn't want to modify the code for that small change because we have already seen in the previous lecture examples, assembly programming examples for Atmega 328P for both for timers and for enabling the interrupts, right? Okay, so after loading, after starting the timer, we also need to enable the timer interrupts, right? So what we are doing is that we are saying, okay, make the OCIE 0 bit, which is output compare interrupt enable bit of TIMSK register, set that bit equal to 1. So basically we are saying enable the output compare interrupt for timer 0, for timer 0. Again, if you remember from the previous lecture, in Atmega 328P, you have three TIMSK registers: TIMSK0, TIMSK1, and TIMSK2 timer interrupt mask registers. But in Atmega 328, you have only one timer interrupt mask register. Okay. Actually, our textbook, it explains all these concepts, for example, interrupt handling using Atmega 328 microcontroller, not Atmega 328P, which we are using in our lab. But again, the concepts are similar. The only difference is that there is difference in registers, their names, and how many registers are associated. But once you know, for example, if you know how you can do the interrupt programming in Atmega 328P, you can also do, you can quickly learn how to do it in for Atmega 328. Okay, so after enabling the interrupt, individual interrupt for output compare, we also need to enable or set the I flag in the SREG status register, right? So for that we are saying set enable interrupt flag, right? Okay, after that we are setting the port C and port D both as the output ports by loading all ones in R20 and then sending R20 to data direction register C and data direction register D. And then we are initializing R20 to 0, right? And then in the main code, we are running a loop where what we do is that we send R20 to port C, and then we are saying increment R20 and jump again. So if R20 was initially 0 on port C, you will have 0, then you increment it and then send R20 again to port C. So you have 1 next time, then you have 2 next time, and so on, right? Up to 255, and then it will roll back to 0. On the other hand, since we have enabled the since we have enabled the interrupt output compare interrupt for the timer 0, we need to write the ISR. So in ISR, remember what we wanted to do? We wanted to increment the value of the value which is displayed on the port D. So first what we do is that we read the value of the port D first. How we read the value of a port? By reading its pin register. So we are reading the pin D register and putting the current value in R20, and then we are saying increment the value, current value, and then send it back to port D, right? Now now the issue is that since you are using the same register R20 to write the value to the port C, and you are also using the register R20 to write the value to the port D, so we will not see the uh, increasing numbers are the numbers displayed in the increasing order on the port C and port D. Why? Because for example, let's say let me change the color. So let's say we were running this, let's say we were here at this time point, uh, and let's say the R20 was 2, right? So now the R20 is incremented and it becomes 3, right? Then you go back here, you are saying jump, here you go back and you display on port C the value of R20, which is 3. Now I am writing here, I'm showing this block to indicate port C. So on port C you display 3, right? Next time what should display on port 3 after this one? 4, right? But you are done with this instruction, but before you reach the increment state, right, what happens is that let's say an interrupt arises and then microcontroller starts executing at this time point. So what will the microcontroller do? It will read the current value of port D, like from pin D register into R20. Let's say the current value of the port D is 10. Sorry. this is D. Okay, so let's say it is 10. So the 10 is loaded from R20, is loaded from pin D into R20. So R20 becomes 10, right? And then it is incremented. So R20 becomes 11. And then you send R20 to port D. So on port D, you see 11, right? And then you go back from the interrupt service routine, return from interrupt, right? So the next instruction that will be executed is this one, right? So here, what you are saying increment R20. What is R20? It is 11. So after incrementing, it will become 12. And then you are saying jump here, and next instruction you are saying display R20 on port C. So on port C, you will see 12. So after 3, you are not seeing 4, you are seeing 12. So this is like resource conflict. Why this is resource conflict? Because you are using R20 both in the code where you are sending the incrementing values on the port C, and in the ISR where you are sending the incrementing values to the port D, right? So that is problem. So how we can resolve this conflict? It is straightforward. I think many of you already have suspected it by simply using a different register. So that is like a straightforward way. So for example, you can say, okay, in this code, in the loop, I will keep using R20, but in my ISR, instead of R20, I can use R21 register. And as a result, now your conflict is gone, right? So you can do that to handle the conflict. But what if there are not enough number of registers available? So for example, let's say uh, uh, you have no more registers available to be used. Let's say you have only single register R20, right? So you cannot use R21. So what can you do? In that case, what you can do is that when you enter the body of the ISR, so before using the R20, before modifying its value, you push its current value to the stack, and then before returning back from the ISR, you pop its value from the stack back into the R20 register. So in that way, you can also again resolve the conflict. So here, when you enter the ISR, you push the value of R20. If we now consider exactly the same scenario which we considered the last time. Let's say the port C had the value of 3, which means R20 was the current value of the R20 was also equal to 3, right? And then the interrupt happened, and now we are in the body of ISR. So what will happen, that R20 will be pushed on the stack. So if it will be pushed on the stack, so let's say on the top of the stack now I have 20, right? And then you are saying, okay, read the value from pin D into R20. Let's say the value of the pin D is just like, if we follow the same previous example, it is 10, right? And then you are saying increment R20, so it will become 11. And now you are saying send 11 to port D. So on D you will have, uh, previously it was 10, and now you will have 11, right? And then before executing return from interrupt, you pop the value from stack into R20. So now when you will pop, it will be, sorry, here I should not have placed 20. Here I should have placed 3, because we are saying pop the value of R20 into the, push the value of R20 on the stack. So now when I say pop, so what happened? 3 will be put into the, back into the register R20, right? Now when you go back here and say increment R20, so it will become 4. And when you say, okay, now go jump back and send R20 to port C, so here you will see 4. So both D and C both are working correctly, because both will show the numbers in incrementing order. Okay. Although both are using the same register, but since we are saving the value of the conflicting register on the in the memory or in the stack by doing the push and pop, so we will be fine. Okay. So that is the second way of handling the conflicting resources. So, but the first one is better or preferable when you have registers available. Uh, but if you don't have enough number of registers available, then you can use the second approach of saving the registers value on the stack. But then it takes time. Why? Because now you are using extra instructions. So for example, how many extra instruction you are using? You are using two extra instructions when you are trying to save the value of only a single register, or when you are trying to resolve the conflict where the conflict is only for a single register. Now assume if there was conflict between let's say three registers, so you will have six more instructions. So it will take more time, right? Now how much more time it will take? It depends upon how many registers are conflicted or how many registers you are trying to push and pop in your code to resolve the conflict. That's why it is not preferable. So whenever it is possible to use other registers, use them. If not, then as a last option, you can save the registers in the stack, on the stack, and then pop them before going back from the ISR. Another issue which we need to be careful while we are writing the interrupt service routines is that we should save status register whenever we change the flags in the ISR. So remember that status register, it is affected by it has multiple flags, right? So for example, overflow flag, carry flag, half flag, sign flag, interrupt flag, and so on, right? So if you are running a main program, if you are running a main program and an interrupt happens, and then you, and let's say then on the when interrupt happen, the control goes to ISR. So the code running in the body of the ISR, it can change the current content of the sreg. So let's say I'm just making some, uh, let me just write it. So let's say that before the interrupt happened, the value of the sreg register was X, right? Which means that different flags had certain values, right? But the 8-bit value was X. And then the interrupt happened and our microcontroller starts running this ISR. So when it runs ISR, it is possible that there are the instructions within the body of ISR which change the values of those different flags in the status register, and maybe its new value, its value is overwritten, current value is overwritten, and new value becomes Y, right? Now when you go back from the ISR to the main program, and the following instructions, they may depend, like let's say it is a conditional branch instruction, right? And the whether that branch is taken or not depends upon the values of the flag in the status register. But what is the right value of those flags? The right value is X, because that is the value before the interrupt service routine was executed, right? But when we come back, the value has been modified to Y. Now maybe the branch which was supposed to be taken with the value of X for the status register will not be taken when the value of the status register was modified to Y by our ISR, right? That's why when we enter the ISR, we first thing we need to do is that we need to save on the stack our S register. So what you can do is you can read the S register into R20, and then you can say, okay, now push R20 on the stack. And in the same way, when you are leaving back, when you are going back, or when you are leaving the ISR, before leaving, you can say you can, yeah, you can pop the value from the stack into the R20, and then write R20 into the register. So here is what is happening. I also spent like a couple of seconds to understand what is happening, and let me explain here what is happening. So let's say this push R20 is why we are doing push R20, actually to handle this situation where we have the register R20 is conflicted between the main code and the ISR. So that's why let's say this is our current stack pointer. So when we are first saying push R20, so let's say the value of R20 is I don't know, maybe let's say its value is 3. So we are pushing 3. So we'll get the value of R20 on the top of the stack, and then top of the stack will be incremented, right? It will be moved, not incremented. Let's say moved is the right word to say. And then we are saying, okay, get the value of sreg into R20. So let's say the value of the sreg at that point was x, right? So in R20 now I got x, right? So now you are saying, okay, now push the R20 on the stack. So now I got x here, right? And now when you are leaving, so you need to do the same thing, but in the reverse order. So you need to pop. So first you are saying, okay, pop R20, pop the value from the top of the stack into the R20. So if let's say in between the value of the here in between the value of R20 was, let's say, changed to something like a. So when you execute this pop R20, so X will be placed in R20, and then you are saying, okay, now write R20 to sreg. So now this let me change the color. Now it will be set equal to X, right? And then after that you are saying pop R20. So when you did this pop, first pop, this was decremented after that. And now on the second pop, this value of 3 will be written into R20, and stack pointer will be decremented again. Okay. So the thing what we have learned here is, like, basically if there is a register which is overwritten by ISR, which is used by the main program, and it is also overwritten by the ISR. So it is our job to make sure that we push that register on the stack when we enter enter the ISR, and pop that register from the stack before leaving the ISR. And the other thing is that we also need to be careful about S register, status register. We need to also push it on the stack while entering the ISR, and pop it from the stack while leaving from the stack from leaving the ISR. Any questions? Okay, if no questions, then with this slide we are done with our topic of handling interrupts in AVR microcontroller, and we are now moving. Sorry. So we are now moving to the next topic, which is about floating point numbers. So uh, what is the problem? So let me first set the context. We have seen how we can represent the decimal numbers in the binary form, right? Or in the computer hardware or digital hardware, how we can represent them. Like for example, you know how to represent one, or 100, or I don't know, any number in the binary form, right? Or let's say negative numbers also. We have seen how to represent, let's say, -100, right? So, but we have not talked about how we can represent the uh, floating point numbers, not floating point numbers. Let me use the numbers which have fractional part. For example, we have not seen how to represent 5.25 in the binary form, and how we can store it in the digital hardware, or how we can represent -4.31, right? Let's say, right? So these numbers are no are the fractional numbers, right? Now the way we can represent them are these are also known as floating point numbers. So how we can represent them in the binary, which basically mean how we can store them in the computer hardware. We are going to discuss that in this lecture. So for example, if you want to store the value of if you want to use pi in your program, and the value of the pi is 3.1415926 blah blah, so how you can represent it in your hardware. So for that, what we do is that we use a different format, or a different approach. So what we do is that we format our fractional numbers, or floating point numbers, by dividing them into two components. One which is known as mantissa, and which is indicated here by M, and the other which is known as exponent, and indicated here as E, right? So again, remember, just like in when we were converting decimal numbers without fractional part, when we were converting them into the binary, we were using the weights, right? So when you have only integer part, which means no fractional part, the weights of the base, which is 2, is either 0 or greater than 0, like it is not negative, right, non-negative. But for the fractional part, the weights are negative, right? So it will become clear when we have a couple of example in next slides. So the weight of the, and here what we use is that the first digit in the mantissa, it has always a dot. So like 1.2 or 1.3 or -1.7, right? So that 1 point, so this first m represents the one in the in our fractional number which we want to represent, right? And its weight will always be 2 raised to power 0, because 2 raised to power 0 is 1, right? For other bits, we will use the negative weights. So for example, the next bit will have a weight of -1, next bit on the right side will have a weight of -2, next bit will have -3, and next one -4. So here we are, remember we said we are dividing our fractional number into two components, mantissa and the exponent, and then we set aside the number of bits that will be used to encode the mantissa part, and those bits, number of the bits which will be used for encoding the exponent. So here if we are saying that we are using only 8 bits in total, so in total we are using only 8 bits to encode our fractional number, right? So 5 bits are used to represent mantissa, and are the m part, and the remaining 3 bits are used to represent the exponent, right? Okay, let me discard these annotations. Now if we have this format, then the maximum value which we can represent is m dot, then 4m bits, these 4 bits, multiplied by 2 raised to power value of these 3 exponent bits, right? So M stands for mantissa, and all the M's here are showed are the bits for the mantissa, and all the E's, they are the bits for the exponent part. Again, we will have a critical concrete example next couple of slides, and it will become clear to you. So for example, if you have this bit pattern, if you have this bit pattern, now 10101011, it all depends upon your interpretation. If you interpret this bit pattern as a regular binary number, so what will be equivalent decimal value, right? So if I consider again, if I consider it as a regular bit pattern, so again I have two choices to consider it as a signed and or as an unsigned. If I consider it as unsigned, so the value will be 1 plus 2. I am writing weights from this side. 1 plus 2, 4 is 0. 1 plus 1, 2, 4, 8, 16 is 0. 32, 1, 2, 4, 8, 16, 32, 64, and 128. So you can do the math, and you will find that this is if we interpret the bit pattern as a unsigned number, so its value will be 128 plus 32 plus 8 plus 2 plus 1. But if I interpret it as a negative, if I interpret as a signed number, so now the most significant bit is 1, so weight will be negative, right? So minus 128, so equivalent decimal value will be minus 128 plus 32 plus 8 plus 2 plus 1, right? And you can do the math and you will find the value, right? The third way, which we are now going to talk about for interpreting, is like we are interpreting it as a floating point number. So if we are now interpreting it as a floating point number, we will use this template or this format, right? And we are interpreting it as an 8-bit floating point number, where we know that 5 bits are used for mantissa and 3 bits are used for giving the exponent, right? So it's mean that we we are simply writing the values here. So this is first bit is 1, the next bit is 0, I'm starting from the left side, next one is 1, 0, and 1, and 0, and 1, 1, and now I simply plug these values into this formula. When I plug the values into this template, so I will get 1 point, and then remember the weights are here negative. So 1 raised to power 1, what is 2 raised to power 0? It is 1. So 1 point, 2 raised to power minus 1 is what? Uh, uh, Wait a minute. Let me erase this thing. So what is this value? It is 2 raised to power minus 1 is so the value of the digit before the dot is 1, and the value of the mantissa after the dot, you can calculate it by just putting the weights. So if you put the weights for mantissa part, so after the dot it will be 0.5, right? This one plus uh, 2 raised to power minus 2 is 0.25. Sorry, because we have the bit here 0. Let me simply erase it, right? So here we have bit 1, so it becomes 0.25. Next bit is again 0, so it becomes 0. Doesn't matter what is the weight because the bit value itself is 0. The value of next bit is 1. So 0.25 divided by 2, it is 0.125. And then when you divide 0.125 by 2 again, so it becomes 0.0625, right? And when you add all these numbers, you will get 1.3125, right? And from where we are getting this 8? From the exponent part. What is the exponent? 2 raised to power 0, 1, 1, right? So, which basically becomes equal to 2 raised to power 3, right? Which is equal to 8. So, 1.3125 times 8, when you multiply, you will get 10.5. Okay. So this is how you can convert a floating 8-bit floating point number with which uses 5 bits for mantissa and 3 bits for exponent. This is how you can convert the bit pattern or the binary form into the equivalent decimal form. Okay. Any questions before we go to the next slide? Okay, if no questions, then let's quickly do an example here and then we will go to the next slide. So using the same 8 bits, where we are using 5 bits for the mantissa and we are using uh, 3 bits for the exponent, what will be the value of, let's say, bit pattern 0, 1, 0, 1, 1, 1, 0, 1? How many bits we have? 3, 4, 5, 6, 7, 8. Yeah. Now do the math and tell me what will be the value in the decimal form. You have 2 minutes while you are doing it on your notebook. I am also doing on my notebook, and let's see the result after that. Is everyone clear on the question? The question is like you have 8-bit binary number, this one, 010111101, right? And this number is a floating point number which uses 5 bits to show the mantissa part, this one, and 3 bits to show the exponent part. So if that is the case, what is the decimal value, equivalent decimal value of this bit pattern? Okay, if you are done with the example and have your answer ready, let me know. I hope you guys are doing the example on notebooks. Anyone who has the answer? If you don't understand, please let me know. If you want me to do the example, I can do that. But you need to let me know that if you don't understand what is a floating point number and how we are converting an 8-bit floating point number. Guys, please give some kind of response. Either tell me like you are done with the example. Okay, good. I think I got it. I got 22. Okay. Yeah. Yeah. Okay. Yeah, 22 is the correct answer. Okay, I can also do it for you on OneNote, right? B13 day 2. So what was the bit pattern? Okay, I have it on my notebook. So the bit pattern was 0 1 0 1 1 1 0 1, right? And we were saying that first 5 bits from the higher side they will be used for mantissa, and 3 bits they will be used for exponent, right? So this bit is basically just to indicate, uh, so it is 2 raised to power 0 into 0 dot 2 raised to power uh, dot, and then we actually simply plus it with 1 into 2 raised power minus 1. Since we have 0, so I can write 0 directly here, and then 1 into 2 raised power 3, and then 1 into 2 raised power minus 4, right? And then multiplied by 2 raised to power 101, which is 5. So here I have 0 plus 0 dot plus 0.5 plus 0 plus uh, 0.125 plus 0.625 multiplied by 32, And now when you will do the math, you will find 22. Okay. Okay, now we have seen that how we can represent a decimal number into the floating point number. But for representing a floating point number into the binary form, we have used only 8 bits, and out of those 8 bits, we have used 5 bits for mantissa and 3 bits for exponent, right? Uh, this the number of bits that we are using to represent the floating point in binary form has some problem. What are those problems? Let's first try to talk about them. Now, if we use the same template or the same 8 bits format, what is the maximum value which we can represent? So the maximum value is when all of these bits are set equal to 1, right? So which is shown here, all ones. Now, if you convert it into the equivalent binary in equivalent decimal form, so and you can do the math, so you will find that it is 242 in decimal, right? So basically it will be uh, so basically here you will get 1, here you will get 0 0.5, 0 0.25, 0 0.125, and here 0.0625. But remember, here you have point after 1. So when you add all of these together, right? Let me do it quickly because then it will help you to understand. So if I add it together, we get 0 0.5 plus 0 0.25 plus 0 0.125 plus 0 0.0625. So we get and then we get 1.9375, right? And then for the exponent part, we multiply it with the mantissa, right? And how you multiply? 2 raised to power 111, but 1 is in binary. So when you convert it into the decimal, so it will get 7, 2 raised to power 7, which is equal to 128. So when you multiply this number with 128, so you will get 248 in the decimal form, right? So this is the maximum number which you can represent, maximum decimal number which you can represent using 8-bit 8-bit binary for floating point representation, where you are reserving 5 bits for mantissa and 3 bits for the exponent. Now, what will be the second maximum number? The second maximum number will be definitely where we set the minimum, the bit which has the lowest weight, we set equal to 0. Which bit has the lowest weight? This bit, right? Because it has weight of 0.0625. So when we set it equal to 0 and everything else is 1, we are reducing it by the smallest weight. So when you will reduce it by the smallest weight and you do the same procedure to find the equivalent, so equivalent decimal value, so you will get the value of 240, right? So actually we said that the second smallest number is 1111011, which becomes equal to 240, right? So uh, the numbers are the issue is that when we use this representation, we are using only 8 bits. There is huge difference between 240 and 248. Uh, and actually the statements that numbers are not equally spaced, it will become clear to you in next slide. So for example, what is the smallest number which you can represent using this template or 8-bit binaries, right? The when you set all the bits equal to 0, this you will get the smallest number, which is 0 in decimal, right? And what is the second smallest number? Second smallest number is when you set the bit for the set the bit equal to 1 for the smallest weight, right, which is 0 0.0625. So when you set this when you have the binary of 0 0 0 1 0 0 0. Then you get the second smallest number, which is 0.0625. So the smallest number is 0, the second smallest is 0.0625, and maximum number is 248, and second maximum is 240. Now the spacing is not same. The difference between 240 and 48 is 8, while the difference between minimum and the second minimum is 0.0625, right? Which basically mean that if you want to represent a number between 240 and 248, let's say 242, you cannot represent using this 8-bit template or 8-bit format, where you have the binary number as size of only 8-bit to represent the floating point number. Similarly, if you want to represent a number less than 0.0625, for example 0.03125, you cannot represent it because the smallest weight is 0.0625 here, right? So that is a problem. Why that is a problem? Because let's say if you are using this 8-bit template in your program to store or to represent the in hardware the floating point numbers, then it's mean that you cannot represent let's say 242.50, right? And you can also not represent, for example, 1.03125, right? S- So this is problem, and from where this problem is arising, because why can't I represent, for example, 0.03125, because I don't have an extra bit here, sixth bit here in my for mantissa, right? So if let's say I said, okay, instead of 8 bits, I'm using 9 bits, right? And out of those 9, I'm using 6 for mantissa. So then here I will have an extra bit, one more bit for mantissa, and the weight of this bit will be 0.03125, right? So the more bits I have, the more smaller numbers I can, fractional numbers I can represent, right? So we will, this is how we can improve the, improve our capability of representing more numbers more precisely. Now, if we compare our 8-bit integers, which we have in, let's say, we were using the bit pattern to represent 8-bit unsigned number, which we are showing here with the blue color. And then the other, if we consider the other case where we are using the 8-bit binary number to represent the floating point numbers, which we are showing here as the this orange colored line, or I don't know, is it red colored line, right? So if you see on the x-axis what we have the 8-bit number value, the 8-bit number index like 0 1 2 3 4 5 up to 255. We can maximum have 255 value in for 8-bit number in decimal form, right? So as we increase the 8-bit number index, the unsigned value also increases, right? So we can represent 0 also, we can represent 0, we can represent 1, we can represent 2, we can represent 4. There is no problem, right? But if we use the 8-bit floating point numbers, what we see is that the gap between the numbers on the smaller sides is is smaller as compared to the gap between the numbers as we go on the bigger side. Like if you remember, the maximum value we have 248 and the second maximum is 240. The difference is 8, right? And the difference between 0 minimum and the second minimum is 0.0625, right? And similarly, the difference between 0.0625 and the next third minimum will be smaller as compared to the difference between second maximum and the third maximum. So the gap starts increasing, as you can see here, for example, right? But the gap in this region is much smaller between the two consecutive numbers represented on the smaller side, right? And this is problematic. Why this is problematic? Because one thing that the size or the gap is not same, one thing, and second, uh, that we cannot represent those numbers which fall between within that gap, like for example a number in between here, right? We cannot represent that number, right? And similarly on the smaller side we will also have problem of representing any number which is falling within the gap. So the issue is how can we close this gap, right? How we can reduce it, not close, but how can we increase it significantly, reduce it significantly. So if the gap is smaller, it's mean that we can represent the numbers, more numbers in the numbers correctly using the floating point form. So for example, we will be able to represent number 242.50, right? How, as I said, if we are able to add more bits here for showing the for the mantissa, and able to add more bits here to for the exponent. I think someone has a question. Oh, okay. Thank you for reminding. Thank you, Mason. So how can we remove that discrepancy, or how we can address that problem? For that, what we can do is that instead of using 8 bits in total, we can use, there are two different solution. One is that where we use a template with 32 bits on total, and the another option is where we have 64 bits in total. Now, the solution which uses 32 bits in total, it offers less precision as compared to the solution which uses 64 bits in total, right? So uh, because using more bits means that we are able to represent more smaller and smaller value, which means we are achieving more precision. So what is meaning of here single precision and double precision? Double precision just means that if you use 64 bits, you are offering more precision, or you are at the second level of providing the higher precision as compared to the case where you are using only the 32 bits in total. Now, since we have quiz, and I don't want to open this topic at this point, because then I will left you in the middle. I will leave you in the middle. I don't want to do that. So let's stop here, and we will talk about these 32-bit and 64-bit floating point numbers format in the next lecture. Okay. Any questions? No questions? Okay, if no questions, then that's all for now. I will be online until end of the lecture, but I'm not sharing the screen anymore. So if you have a question or anything at the lecture time, you can ask me.